Okay, second video, we're going to focus on 4 gas laws. And gas laws basically tell us how when variables change, how they're related to each other. So the first one we're going to start with is called Boyle's Law. And Boyle's Law states that the volume of a fixed amount of gas held at a constant temperature varies inversely with pressure. Okay, so what we're looking at is we have some gas. We're not changing how much there is. We're not changing the pressure. We're only changing the volume of the container, and we're looking at how the pressure changes. And Boyle's law says that they vary inversely, meaning if, and you can look at the pictures to see this, if we decrease the amount of volume, right, so we move it into a smaller container, the particles are closer to, they're in a closer space, they're in a smaller space, so they're going to collide with the container more often, which means the pressure goes up. So as the volume decreases, the pressure increases. And our formula for Boyle's law is P1V1 equals P2V2. So if we multiply pressure times volume, if one goes up, the other has to go down to keep that constant. Okay, and that's what it's showing you here. And this is what our graph would look like. If we were to graph pressure versus volume, as we are decreasing the volume, okay, then our pressure is increasing. Now, we want to do a calculation with this, okay? When we are doing calculations with gas laws, there are basically 4 variables we're going to work on. We're going to work with pressure, which needs to be in atmospheres. We're working with volume, which has to be in liters. We're working with temperature, which has to be in Kelvin, and we're working with number of moles. Okay, so those are the 4 main variables we're going to be looking at. Now, in Boyle's law, the number of moles and the temperature aren't changing, so it's just the pressure and the volume that we're going to focus on. So the hardest part about this chapter is not the math itself, it's figuring out which gas law to use. So my suggestion is when you're reading a problem, write down everything that's given. And based on what you're given, that's going to help you pick which gas law is appropriate. So here it says a diver blows a 0.75 liter air bubble 10 meters underwater. As it rises to the surface, the pressure goes from 2.25 atmospheres to 1.03 atmospheres. What will be the volume of air in the bubble at the surface? Okay, so we are given some initial volume. So we'll say V1 equals 0.75 liters. Okay, and then it tells us the pressure is going from 2.25 to 1.03. So our initial pressure, P1, is 2.25 atmospheres. And our P2, our new pressure, is 1.03 atmospheres. So then our question says, what will be the volume of air? So we're going to solve for V2. So as you can see, we're only given pressures and volumes, which means we're going to use Boyle's law. So Boyle's law says P1 V1 equals P2 V2. Okay, and these are multiplied together. So if we put in all of the variables that we know, our P1 is 2.25, our V1 is 0.75. That's going to equal P2, which is 1.03, and V2 is what we're trying to solve for. That's our unknown variable. So if we want to solve for V2, we need to divide by 1.03. So when we divide, we keep 2 sig figs because of the fewest in the problem. When we divide, we are going to get 1.6 liters. Okay, our next law is called Charles' law, and Charles' law states that the volume of a given amount of gas is directly proportional to its Kelvin temperature at constant pressure. So this time we're going to be looking at volume and temperature with the pressure being held constant. So basically what that means is as the temperature increases, the volume of the gas will increase to keep the pressure the same. Okay, so because the particles are moving faster, they have to be in a bigger container, otherwise they're going to collide more often and cause the pressure to go up. So if we want to keep the pressure constant, as the temperature increases and the particles are moving around, we have to put them in a bigger container, otherwise they collide more often. Now in this particular formula, we're using temperature, and the temperature has to be in Kelvin. If it's not in Kelvin, if it's in Celsius, we could have negative values, and you can't have negative volume, so you can't use negative temperature. You have to use Kelvin, so that way we always have positive numbers. And if you remember, it can't go lower than 0. Absolute 0 is 0 on the Kelvin scale, so your temperature always needs to be in Kelvin. And if you don't remember how to get Kelvin, you have to add 273 to Celsius to get Kelvin, and we'll see that in some of our examples. All right, so here's our visual. Okay, if you can see here, we have some volume and some temperature. As the particles start moving faster, their pressure is going to go up unless we put them in a bigger container. Okay, and because they are directly related to each other, as one increases, the other increases, then in our graphs you can see that we get that line where they're both going up. All right, let's look at our example here. So it says that a helium balloon in a closed car occupies a volume of 2.32 liters at 40 degrees Celsius. If the car is parked on a hot day and the temperature inside rises to 75 degrees Celsius, what is the new volume of the balloon, assuming the pressure remains constant? Okay, so like we did before, let's write down all of our variables. So we have our initial volume, so we'll say V1 equals 2.32 liters, and then T1 equals 40 degrees Celsius, which we need to convert to Kelvin. So we're going to add 273, which is going to give us 313.0 Kelvin, just capital K Kelvin. All right, and then it says the temperature inside rises, so that means our T2 is 75.0 degrees Celsius. Again, add 273. So our T2 in Kelvin is 348.0 Kelvin. And then the V2, that's what we're trying to find. The question says, what is the new volume? So V2 is our unknown. Okay, so Charles' law says V1 over T1 equals V2 over T2. Okay, so we know V1, 2.32 liters, over T1, 313.0 Kelvin, equals V2, that's our unknown variable, over T2, 348.0. So to solve for V2, we're going to divide, we're going to multiply by 348, use your algebra skills, and our V2 with 3 sig figs comes out to 2.58 liters. So as the temperature went up, the volume also went up. Okay, next gas law is called Gay-Lussac's law, and it states that the pressure of a fixed amount of gas varies directly with the Kelvin temperature when the volume remains constant. So kind of like we saw with Charles' law, as we're heating up the gas particles, they're going to be moving faster and colliding more often. So if the volume of the container doesn't change, if the volume stays constant, then the increase in temperature will increase the pressure. Because we are colliding the particles more often. So in our container, you can see they have the same volume, but as we increase the temperature, the particles are moving faster, they're colliding more often, and the pressure goes up. So they are directly proportional to each other. Okay, let's work our problem here. It says the pressure of the oxygen gas inside a canister is 5 atmospheres at 25 degrees Celsius. The canister is located at a camp high on Mount Everest. If the temperature there falls to -10 degrees Celsius, what is the new pressure inside the canister? Okay, let's list our variables. So we have our initial pressure. So P1 is 5 atmospheres. And it tells us the initial temperature is 25 degrees Celsius, which we need to convert to Kelvin. And that's going to be 298.0 Kelvin. The temperature goes down, so our T2 is now negative 10 degrees Celsius. So this is why we can't use Celsius. You can't have negative numbers when you're doing these calculations. So if we add 273, that's going to give us 263.0 Kelvin, so our T2. And then we want to find the new pressure. So P2 is our unknown variable. All right, Gay-Lussac's law, P1 over T1 equals P2 over T2. Okay, so P1, 5 atmospheres. T1, 298.0 Kelvin. P2, that's what we don't know, so that's our variable. And T2 is 263.0 Kelvin. So, divide over here, multiply by 263, use your math, solve for P2, which will be 4.41 atmospheres, keeping our 3 sig figs. So as the temperature went down, so did the pressure. All right, our fourth gas law is called the combined gas law, and it shows how all 3 variables are related to each other. So the pressure, volume, and temperature are all changing. The only thing that's not changing is the number of moles, how much gas we actually have. And actually, this is really the only gas law you need to know, because if you're given a problem where, for example, pressure and volume change and the temperature is held constant, if you were to take the T's out of here, okay, then you would get Boyle's law. So you really don't have to memorize all of the formulas. You just need to memorize this one and take out the variables that are held constant and just use the variables that are changing. If volume is held constant, take out the V's. If pressure is held constant, take out the P's, and you have the other 3 variables. So don't look at it as a fourth gas law, look at it as the combined gas law that can help you figure out all of the other ones, okay? All right, so I want you to work out this particular problem and see if you can come up with the right answer. So I want you to pause, and then when you are finished, come back and I will tell you what the answer is, and hopefully we got everything correct. Now, couple of things you need to pay attention to. 1, pressure is not in atmospheres, it's in kPa, but both of them are in kPa, which is fine. If you have 2 pressures, they have to be in the same unit, so we don't have to do any conversions with pressure there. You can use kPa. Second thing, pay attention to your temperature. It's given in degrees Celsius, so make sure you convert to Kelvin. All right, I want you to pause. I want you to work the problem. Pay attention to your units, and then come back and see if you got it right. Okay, let's see. So our final answer, wanting to know the new volume, your final answer should be 0.583 liters. Hopefully that's what you got. If not, go back, figure out what you did wrong, or come see me in tutorials.